Hi everyone, good day. Today we are going to see the last topic of the second unit in the course, Cryptography and Network Security. This course is developed by Jawaharlal Nehru Technological University, Kakinada, in association with Andhra Pradesh State Council of Higher Education. So before we start with Advanced Encryption Standard, what happened before that? That is what we're going to see the history of Advanced Encryption Standard. Why are they named it as Advanced Encryption Standard? So in the last lecture, we have seen about data encryption standard, and we have seen the drawbacks of data encryption standard. So due to the drawbacks of data encryption standard, the National Institute of Standards and Technology, that is NIST, want to replace DES with a strong algorithm. So they named that algorithm as Advanced Encryption Standard algorithm. They have not found any procedure, and they have given a open call for the algorithms. They have given an open call for the algorithm by specifying some specifications. The specifications are: it should be of a block cipher, it should be a block cipher, and the block size it should accept is 128 bits, that it should take input as 128 bits, and it should come in three variants with three different key sizes. Those are 128, 192, and 256. So these are the specifications provided by the NIST. So along with it, they have given some criteria also. The algorithm that come to them, they satisfy three criteria. Those are security, cost, and implementation. So when you are given the open call for this advanced encryption standard, there are about 21. They have received about 21 documents. Out of those 21 documents, they have shortlisted 15 initially. Then from those 15, they have checked for this key size and block size and the security, cost, implementation, and they have shortlisted 5. And finally, they have conducted a conference, and they have finally approved one algorithm developed by Belgium researchers John Dayman and Vincent Regiment, and they selected it as advanced encryption standard. So initially, when the algorithm is developed by these Belgian researchers, they call it as Rinsendal. We call it as what? Rinsdal. So the Rinsdal is later renamed as Advanced Encryption Standard. So this Rinsdal algorithm satisfies all the criteria of this AES algorithm that they have given by the NIST. So what does these three criteria says? So security says the main emphasis was on security because NIST explicitly demanded a 128-bit key. Why? Because previously in the DES we have taken 56-bit, and then we have gone for double DS. Both have vulnerable to the known plain text attack, as well as the double DS is vulnerable to the meet in the middle attack. So that's why they need a key which is of so long. So that's why they are considered as 128-bit key, and up to now there is no attack that is proven on this 128-bit key of AES. Now coming to the cost, the second criterion given by the NIST is about cost, which covers the computational efficiency and strong requirement for different implementations, such as like we can implement using hardware, software, or some smart cards. Then they have gone for the implementation. The criteria include the requirement that algorithm must be flexible in order to it can be implemented on any platform. So the algorithm given by the Belgian researchers Rinsdal satisfies all the three criterions, and finally this Rinsdal is considered as advanced encryption standard. So first we'll see about advanced encryption standard. So advanced encryption standard is an symmetric block cipher. AES is an symmetric block cipher, but it is unlike DES. DES is an feastal cipher. AES is a non-feastal cipher. So what is the difference between feastal and non-feastal cipher is? In the feastal cipher, we consider some like invertible, self-invertible, as well as non-invertible components, whereas in non-feastal ciphers we consider only invertible components. So we can say AES is a non-feastal cipher that takes in 28-bit input and produces 128-bit output. It takes 128-bit input and it produces 128-bit output. But the key size depends upon the number of rounds that we are considering in the AES. The key size depends upon what? Number of rounds that we are considering in the AES. So AES comes with three different varieties. Those are 10 rounds, 12 rounds, and 14 rounds. These rounds depends upon the keys. So if you are considering a 128-bit size key, the number of rounds will be 10. If you are considering a 192-bit size key, the number of rounds will be 12. If you're considering a 256-bit size key, the number of rounds will be 14, and the vice versa also. Depending upon the rounds, we can also choose the key. So here it happens like this. So it takes, if you consider this as a AES block, this entire thing is AES block cipher. It takes 128-bit plain text and it produces 128-bit cipher text by using an 128 or 192 or 256-bit cipher key, and the cipher key size depends upon number of runs that we are having in the block cipher. Okay, now for each round we are saying it processes to 10 number of rounds or 12 or 14, depends upon the key size. Each round requires an round key. Unlike there in the DES, we take the actual cipher key size is 56 and the round size is 48. But here the round size is 128, which is exactly equivalent to the plain text size, or exactly equivalent to the cipher text that we are creating. Right? So if you observe, the 128 round key we are supplying to the each round. Right, each round. So one more thing there, in DES, when we have 16 number of rounds, by using the random key generator, we have generated 16 round keys. But whereas in AES, it is unlike DES. In AES, when we have n number of rounds, we need n plus 1 keys. We need 1 plus 1 keys. N will be used for the n rounds. N will be n keys that is generated from the key expansion will be used for n rounds. The remaining 1 key will be used for the initial pre-round transformation. Will be used for what? Pre-round transformation. This pre-round transformation is nothing but add round key. So this is abstract about AES algorithm. Now we will see about some data units that we are going to use in AES. If you observe here, we are using key expansion, not key random generation. Remember that one. Whereas in DES we'll have key random generation, but whereas in AES we'll take the cipher key and we expand it for generating the round key, 128-bit round key. Remember that one. Okay, now we'll see about data units. The first data unit that we consider in AES is bit. So we all know about bit. So bit is a binary digit with a value 0 or 1. So we use a lowercase letter to represent bit. Then is byte. So a byte is a group of 8 bits. And we can represent this byte by using a capital B, and we can make this bit in the form of a row matrix, or we can represent in the form of a column matrix. So if I want to represent this byte by using an row matrix, simply I can represent like this. So the size of this row matrix is 1 by 8. That is, I'll have 1 row and 8 columns. Or else I can also maintain this byte in the form of an column matrix. I also maintain this byte in the form of a column matrix, where I'll have 1 column and 8 rows. This is how I can represent the byte. So the next data unit that we are going to consider in AES is word. So a word is a group of 32 bits. A word is a group of 32 bits that can be treated as a single entity or a row matrix of 4 bytes. So we are saying byte is 8 bits. So we represent a word like this. So byte 0, byte 1, byte 2, and byte 3. So now how we can represent, byte 3, not 4. This is how we can represent a word. So it can represent a word in the form of a row matrix where each will have 4 bytes. That is 1 byte, 1, 2, 3, 4 bytes. Totally 4 8s, 32 bits. Okay, or as a column matrix also. The same thing we represent in the form of column matrix also. When it is treated as a row matrix, the bytes are inserted into the matrix from left to right. When it is considered as a column matrix, they are inserted from top to bottom. So if you're representing in the form of a column matrix, if you're representing word in the form of a column matrix, this will be like this: B0, B1, B2, and then B3. Okay, this is how we are going to represent it as a column matrix. If we are representing word in the form of a row matrix, this is how we are going to represent it. So word is going to be represented by using the letter W. Word is represented by the letter, bold letter W. Okay. Now we'll discuss about the next data unit, that is block. So AES encrypts and decrypts data blocks. So it takes input as a data block and it produces output as a data block. It produces an output as a data block. So a block in AES is group of 128 bits. However, a block can be represented as a 16-byte row matrix. You can represent a 16-byte row matrix, right? So this is how we represent a block. Sorry. So if you take this as a, so now we can take 0 to 15, 0 to 15 bytes. So we can take, so this is byte 1, so on up to byte 16. So we can represent the block that we take the input as 128 bit. That 128 bit can be represented as 16 bytes. 16 bytes. So we come across block in AES at the starting stage and the at the last, when you are taken plain text, we can consider it as a block, and when given ciphertext, we consider it as a block. But meanwhile, in the middle stages, we consider that as a state. We consider it as a state. So AES uses several rounds in which each round is made of several stages. We'll see what are the stages that we have in the round in the next last slide. So data block is transformed from one stage to another. At the beginning and end of the cipher, AES uses the term called as block. Before and after the stage, the data block is referred to as a state. That's what a before and after stage, the block data block is referred to as a state. We use an uppercase bold letter S to represent the states. So we'll see how we are going to represent, and state is going to be represented by using an 4x4 matrix. Remember, state is going to be represented by using an 4x4 matrix. I'll show you how we are going to convert a block into a 4x4 state. 4x4 state. Okay. Now we'll see some samples for this byte, right? So this is the byte. So this is the byte. So we are having 8 bits. We are having 8 bits. So this is an row matrix. How we are representing a byte. This is how we are representing a byte in the column matrix. Now this is word. So this is how we are representing word using a row matrix, and this B0 refers to a byte, that is 8 bits. So like similarly, this is column matrix, this is block, how we are going to represent the block. Here each B0 is representing a byte. So totally how many bytes we have up to B0 to B15? Is totally we have 16 bytes. So each of it 16 bits. So 16 into 8 is 128. 16 into 8 is what? 128. This is how we represent the plain text. Now, this plain text will be converted. This plain text will be converted initially into a state. So state is also representing 4 by 4. 4 by 4. Now, I'm saying now we can also represent this as a word. We can consider this as a word. So here, the word is represented as a column matrix. The word is represented as a column matrix. This is word 0, word 1, word 2, word 3. Okay, remember? So the data from the block we can convert into a state, and the data within the state we can consider it as a word. So every column in the state we consider it as a single word. Every column in the state we consider it as a single word. So totally this is 4 by 4, and each will have capacity of a byte. Okay. 4 bytes. So totally we'll have 16 bytes. So 16 into 8, 128. Similarly, we have words here. How many words we have? 4 words. So 4 into what is size of the word? 432s. So here also we'll have 128. So everything we discuss here will be related to 128-bit plain text. 128-bit plain text. Why? Because AES takes 128-bit plain text. Okay. Now we'll see about what happens within the round, or we'll see how we are going to convert the given block into a state, and again how we are going to convert the given state into a block. Okay. Now if we consider this is the block given to you, how we are going to do is the first 4 bytes. The first 4 bytes will become the first column. The next 4 bytes will become the second column. Next 4 bytes will become the third column, and the last 4 bytes will become the fourth column. This is how we are going to convert the given 128-bit plain text into a state. Like this we are filling. See, you are saying like this. So B0, B1, B2, B3. Again, we'll start at top. B4, B5, B6, B7. Again, we'll go to the stop. B8, B9, B10, B11. We are done. Then again, we'll go to top. B12, B13, B14, and B15. Now, while we are converting this into a block, we are converting a state into a block. Simply, we'll write in this order. So the first column will be written. So B0, B1, B2, B3, followed by the second column, B4, B5, B6, B7, followed by the third column, B8, B9, B10, B11, and finally the last column, B12, B13, B14, and B15. So this is one example showing how we are going to convert. So this is plain text. So A, E, S, U, S, E, S, A, M, A. Now this will be converted into its hexadecimal values. So 00, 04, 12, 14, like that. They'll be converted into their hexadecimal values. Now we are going to convert this into an state. So I told you, the first four will be considered as the first column. So 00, 04, 12, 14. The second four will be considered as second column, right? So second column, 12, 4, 12, 0, 0. The third four will be considered as third column. So 0C, 00, 13, 11. It will be considered as third column. And 08, 23, 19, 19 will be considered as fourth column. This is how we are going to convert the given input plain text into a state. Input plain text into a state. Okay. Remember this one. Why? Because at the starting stage and the last stage, we'll do this one. In the middle stages, we'll consider the data as state. Okay, so now we'll see about each round, structure of each round. Now in each round, we'll have four operations mainly. Each round consists of four operations mainly. So they start with shifting rows, and then substitution bytes, mix columns, add round key. Okay, add round key. The same thing we'll do it in the decryption also, but they're all inverse operations. They all are inverse operations. There we call it as inverse substitution byte, inverse shift rows, inverse mix columns, and add round key. There we doesn't call it as inverse add round key. Why? Because add round key itself is a self-invertible component. Add round key is at a self-invertible component. So if you see here, each round we are going to do four operations. And remember one thing, in the last round of encryption, mix columns will not be there. In the last round of encryption, mixed columns will not be there. So up to the last but one round, we'll do these four operations. We'll take the state, we'll apply the substitution bytes, we'll get a again state that will be given to the shift rows. Again, we'll get a state that will be given to the mixed columns. And finally, we'll give the state to the add round key. Here, where you are using the round key, that is 128-bit round key. That is what? 128-bit round key. So one add round key is applied before the first round. I told you, we will generate, if you have n number of rounds, in AES, we are having, we will be generating, or we'll be producing n plus 1. We're getting 1 plus 1 round keys. So we are using n keys for the n rounds, and this one key will use at the initial stage of the AES, that is before the first round. And the third transformation is missing in the last one, that is mix columns will not be there in the last round. Mix column will not be there in the last round. Okay, this is how the encryption takes place. And all other functions at the decryption side, we call it as inverse mix columns, inverse shift rows, inverse substitution bytes, but we call it as add round key only. Why? Because add round key is a self-invertible function. Now we'll consider each operation or each transformation one by one. So the first one is substitution. The first one is what? Substitution. So to provide security, AES uses four types of transformations: substitution, permutation, mixing, and key adding. So substitution, we have done it by using sub bytes transformation. Permutation, we are going to do it by using shift keys. Mixing, we are going to do it by mixing with a constant matrix, multiplication each byte with a constant matrix. We're going to see it. And key adding is that sorry, where key adding is the process where we add the round key finally to the state. Now we'll start with the first transformation, that is substitution. So the first substitution done for each byte. Second, only one table is used for transformation for every byte. So if you are having 2 bytes in common, in the plain text, we'll get the same transformation. So the transformation is defined by either a table lookup process or mathematical calculation, but generally we will go for table lookup only. If you go for mathematical calculation, again we need to go for the concept of Gauss field of prime numbers, that is gf of p power n. You should go for that polynomial. So basically we'll go for table lookup only. So the first transformation that going to do substitution is substitution bytes. We call it as sub bytes, is used at the encryption side. To substitute a byte, we interrupt the byte as 2 hexadigits. We interrupt the byte as what? 2 hexadigits. So the left digit defines the row number and the right digit defines the column number. Whatever we are getting, that interception of these 2 bytes, that is at the row side and at the column side, that will be the substitution for that one. Like this. So for example, if I want to substitute this bit, if you want to substitute this byte, if you want to substitute this byte, what I'll take is whatever the value I have in this byte, I'll take that. Now its corresponding value. Consider I have here 2 and f. The value here, it is what? 2 and f. Now what I'm going to have a substitution sub-bytes table. Now how I am going to substitute this value is, as it is 2f, the first one tell me about the row and the second value will tell me about the column. Now what happens? I'll go to the second row. And f column. Maybe f column will be last. No, f column. So whatever the value I'm getting at the intersection, I will replace this value with this value. The main thing that we need to consider is the substitution table that we are considering. Okay, so let us see an example of substitution table. Okay, so this is the substitution table. For example, what is the value that we have considered? The value I considered is substitute is what? 2f. Let us consider with what value it will be replaced. So the value I'm considering is 2f. So if I use this sub-bytes table, this will be replaced with what? So which row I need to see? I need to see the second row. And what is the column number I need to see? I need to see the column f. Now what is the value that I have at the intersection of second row and f column? It is 15. We cannot call 15, 15. It is 15. So in the first, that is sub bytes transformation, my 2f value will be replaced by 15. So this is how the first transformation of the AES round is done. That is what? Substitution bytes. Like this, each byte value will be replaced by an other byte value. Then we'll go for the second. What is the second thing we have seen in the round? Shift keys. The second one is what? Shift rows, where we'll do the permutation operation. So another transformation found in a round is shifting, which permutes the byte. So unlike DES, in which permutation is done at the bit level, here transformation here is done at byte level. The order of bits in the byte is not changed. So we'll replace. So for example, in DES, if we consider bit 1, bit 2, bit 3 and bit 4, then we have applied the transformation on these bits. But here we are going to do it on the byte. So consider 0 to 7. Consider 0 to 7 is my first byte, right? 8 to 15 is my second byte. Like that, what I'll do is I'll consider this byte as 1 unit. Now I will shift this byte, but the bits within the byte will not be changed. The order in which the bits reflect, they will be in the same order. They will be in the same order. So this permutation will be done by using shift rows. Shift rows, whatever the operation we have. So in the in the subbytes also, we'll have the inverse of the subbytes in the decryption. In the same way, whatever the thing we have in the shift rows, the same thing will have it in the decryption. That is inverse shift rows. Inverse shift rows. Okay. Now, so if you observe, by how many bits we need to shift it? By how many bits we need to shift it? So we take the state that came as out input from the substitution bytes transformation. You'll take it as input. Now, depend upon on the row number. If it is row 0, we'll have no shift. We'll have no shift. If it is row number 1, we'll have 1 byte shift. If it is row number 2, we'll have 2 byte shift. If it is row number 3, we'll have 3 byte shift. Remember, we are saying shift. This shift is what? Circular shift left. This is what? Circular shift left. The opposite of shift left is what? Shift right. It will be done in the decryption. We all know that encryption and decryption are two invertible processors. So whatever the operation that we are doing in the encryption, the inverse operation should be done in the decryption. So in the decryption side, when you are saying it as inverse shift rows, it will be right shift right. In encryption of AES, it is shift left. Now we'll see an example here. So this is what we are getting. This is the state that we are getting as input to the shift rows from the substitution bytes. That is sub bytes. Now we need to check. So this is the first row. So there is no shift here. It will be like as it is. So 63 C9 FE 30 FE 30. Now this is regarding the what? First row. If it is first row, by how many bytes it should shift left? It is should circular shift left. It is should done by 1 byte. It should be done by 1 byte. So this F2 63 26 F2, right? F2 63 26 F2. Now coming to this row, it is row number 2. So it is row number 2. It should be gone for 2 byte shift. It should go for 2 byte shift. So 70 will come here. So 70 comes here, and D4 comes here, and these two values will be C9. So 70, D4, C9, C9, right? Same values we got. Now, if we go for the third row, we need to have 3 byte shift. So it will be D4, FA, 63, 82. If you observe, the values are as it is for the bytes. So we said that when we are doing the shift byte, the values within the byte or the bits within the byte will not be changed. They'll remain as it is. That's why if you see here, the byte values are as it is, but the order of the bytes has been changed depending upon their row number. Depending upon their row number. This is how shift rows is done. So the shift rows output will be given to the next transformation, that is mixing. That is what? Mixing. So what happens in the mixing? If you observe substitution bytes in a intra-byte transformation. Is what? Intra-byte transformation. Whereas shift rows is byte exchange transformation. So the mixing transformation changes the contents of each byte. Here, the contents are not changed. Purely, they are not changed. So to change the contents entirely, what we'll do is in the mixing, we'll take a constant matrix. We'll take a constant matrix, and we'll consider an column from the given state. Each column from the given state, and we multiply each column that we are considered from the state with the constant matrix, and we'll get a value. And again, this value will be replaced as a new column. This value is replaced as a new column. Okay. Now, for this mixing, we can consider if you consider C as a constant matrix at the encryption side, at the decryption side, we'll convert it C inverse. We'll take it C inverse. Okay. Now, if we consider the mixed columns will be depicted, the scenario will be depicted like this. So if I take this column from the state, I'll take this column. Now this is my constant matrix. I'll apply multiplication with this constant matrix. Now when I apply multiplication with the constant matrix, I'll get again a constant. So we have learned in the matrices of first unit where you are considered mathematics of cryptography. So what is the size of this matrix? What is the size of this matrix? It is a column matrix, so it is 4 by 1. It is 4 by 1. Now, what is the size of this one? 4 by 4. What is the column size that we are considering from the state? It is what? 4 by 1. So when we apply in multiplication between 4 by 4 and 4 by 1, we are going to get a 4 by 1. Now, with which column we have considered from the state, that will be replaced by the output. That will be replaced by the output. That will be replaced by the output. So this constant matrix will be taken before only. Okay, this constant matrix will be taken before only. Now, whatever the constant matrix we are considering here, whatever the constant matrix we are considering here, the inverse of that constant matrix should be considered in the decryption process. This is very thing you need to remember. This is the very good thing you need to remember. So if you see, this is C and this is the C inverse. The mixed columns transformation operates at the column level. That's we have seen. So it considers each column from the given state, which is an input to the mixed column and output of shift rows. It transforms each column of the state to a new column. So how it's going to transform is, it picks off each column from the state and multiplies with a constant matrix, and it will get a new column for that as an output. So simply it replaces the taken column with the output column. So if the two constant matrices are inverse of each other, it is easy to prove that the two transformations are inverse of each other. This is how the mixed columns or mixing is done. The mixing operation is performed by mixed columns in the round of AES. Next is add round key. So first we'll see how we are going to add round key, and then we'll see how we are going from 128 or 256 or 192 cipher key, how we are generating the 128 round keys different. That is n plus 128 bit round keys from. So depends upon that expansion. Okay, expansion. So before that, we'll see the last stage or last transformation in the round, that is add round key. So add round key also proceed one column at a time, but the difference between mixed columns and add round key is that in mixed columns we'll do the multiplication, whereas in the add round key we'll do the addition. Okay, remember that one. So here also in add key also we consider column at a time. Here also we consider column at a time. If you observe, here we're considering a column. From the state, and we are taking that column and we are taking a key. So how we are taking? So for the addition, we should be having the same. No, that's why we are taking the same values. So how we are going to arrange the key? So key is also of 128 bit, right? Each round key, I'm speaking about each round key. The cipher key may differ, so it may be 128 or 192 or 256. It may differ, but one thing I told at the starting of the AES abstract view, that the round key size will be 128 bit for the AES, whatever may be the cipher key size. We doesn't bother, but the round key size will be 128. So as it is 128, we can convert this into an state. Which is of 4 by 4 matrix. That is 4 by 4 matrix. We have 4 columns. Now what we'll do is, I'll take the first column of the state. I'll get the first column of the state, and I'll take the first column of the keyword. I'll add them. I'll get an new column and I'll replace it with it. That's what happens here. Okay, Okay, now consider the key as 4 columns or 4 words. Now what happens? I'll pick this first word. Pick first word, and I'll take this first column from the state. I'll apply the XOR operation between them. The resulting will be taken as the first column. Now again, I'll take the second row. Second column or second word from the key. I'll do XOR operation with the second column from the state. The output will be the second column of the output state. Like that, I'll do the add round key operation is done. Okay. This is add round key operation. So if you observe if you observe, out of these 4 transformations, that is substitution bytes, we are doing at a byte level. We are taking a single byte and we are following a table and we replacing. That is like byte substitution. Whereas in the shift rows, simply the word, the row is simply shifted by number of its row size. But whereas in mixing columns, whereas in add round key, we are considering the columns. So in the mixed columns transformation, we do multiplication with each column with a constant matrix, whereas in add round key, we do addition between the first column of the state with the first word of the key. That's how the add round key process. Now we'll see about the key expansion. Okay. Now, whenever we are given an 128-bit cipher key, consider whenever we are given an 128-bit cipher key, we need to generate how many subkeys is what. So if my cipher key size is 128, the number of rounds are 10 rounds. The number of rounds are what? 10 rounds. Okay. Now, for the initial round, that is before starting round, we'll have an add round key, right? We'll have add round key. For that round key, I'll take the initial as my round key. So this is my so if consider this is my cipher key. So K0, K1, K2, so on K. These are all my bytes from the given key. Right? Now for the first one, that is in the encryption, before the round starts, I need to have an round key. Which applies the add round or pre-round transformation. For that, I'll take this first as it is. I'll take the key as it is. Okay, I'll take the key as it is. We call them as word 0, word 1, word 2, word 3. I'll call them as what? Word 0, word 1, word 2, word 3. After that, I'll follow 2 rules. I'll follow to generate this round key. So the rules are like this. The first 4 words are made from the cipher key. First words are from, because I told you pre-round key. Now the cipher key is thought of as an array of 16, K0 to K15. The first 4 words K0 to K3 will be considered as pre-round. Key 128. Now the rest of the words will be generated like this. So Wi for I is equal to 4 to 43 is made if I mod 4 is not equal to 0, Wi is equal to Wi plus 1, I minus 1 XORed with Wi minus 4. If the I mod 4 equal to 0, Wi is equal to T XOR Wi minus 4. So we will consider about temporary word. So before that, we will see what happens if I mod 4 not equal to 0. I mod 4 not equal to 0. So for all these things, for all the starting things, I mod 4 equal to 0, right? For all the, so for W4, I mod 4 equal to 0. For W8, I mod 4 equal to 0. For W40, I mod 4 equal to 0. So we'll check how we are going to get these W4, W8, and W40. Before that, we'll see about the words which are having mod not equal to 4. So if I take 5 mod 4, what is the value? 1, which is not equal to 0. If I take 6 mod 4, what is the value? 2, which is not equal to 0. For all these things, how they are getting is I'll take Wi minus 1. So I'm taking Wi is W5. So W4, I'll take W4 XORed with Wi minus 4. So 5 minus 4 is what? W1. So I'll get W5 by XORing W1 and W4. By XORing W5 and W4. Similarly, if I consider W7, so what is 7 mod 4 is 3. It's not equal to 0. So what should I get? How I am getting W7 is W7 I'll get Wi minus 1, that is W6 XORed with Wi minus 4. What is W7 minus 4? W3. So W3 is XORed with W6 for generating W7. So remember, so first whenever we are given an 128-bit key, we'll take it as 4 words. We'll consider it as 4 words. So initially the 4 words will be taken as first round key. Initially, the first 4 rounds will be taken as what? Initial round key. From thereafter, the next round keys are generated. So how the round keys are generated is, so we'll consider the round key value, the word, by using one thing, that is mod 4 operation. So if wi mod 4 equal to 0, we'll do one operation. If wi mod 4 not equal to 0, we'll do one operation. So w5, if it is wi mod 4 is not equal to 0, then we'll make wi is equal to wi minus 1 XORed with wi minus 4. Now, now we'll see if wi mod 4 equal to 0, then we'll take if we'll take a temporary word called as t. We'll take a temporary word called as t. We'll take a temporary word called as t. Now, how we are getting this temporary word? How we are getting this temporary word t is what? By applying 3 operations. By applying 3 operations. Those are rot word. We're applying rot word and then substitution word. The output will be XORed with R constant. Will be XORed with R constant. So what is this rot word? Rotate word routine is similar to the shift rows transformation, but it is applied to only one row. It is only applied to only one row. Okay. Similarly, subword. The subword routine is similar to the substitution by transformation, but is applied only to 4 bytes. It is applied only to 4 bytes. In the 4 bytes, right? We'll use the substitution word, whereas round constant, each round constant or constant is a 4-byte value in which the rightmost 3 bytes we have. So this is the round key. This is the round constant we consider. So for round 1, this is the round constant. For round 2, this is the round constant. For round 3, this is the round constant. For round 4, this is round, like that. For every round, we'll have a round constant. Out of this, okay, out of this, in which the rightmost 3 bytes are considered. Okay, value in which the rightmost 3 bytes are considered. So all is like this. Okay, the 3 bits are not considered, only the left, right, the fourth one is considered. So like this is called as round constant. Now whenever we get this one, what we'll do is, first we'll apply rotate word and wi minus 1, and then we'll apply substitution word, and then we'll apply XOR with the R constant value. We'll apply the R constant value. Now for all the values which are divisible by 4 exactly, we'll do this one. So for example, if I see w4, so here wi mod 4 equal to 0. So if I having wi mod 4 equal to 0, what I need to do? I need to do XOR operation between temporary word t4 and wi minus 4, that is w naught. So how I am going to get t4 is by applying 3 operations. What are those? By applying rotator word on wi minus 4, that is on w naught. Okay, and then applying the substitution bytes, and then applying XORing with the R constant, row constant. No, by applying with the row constant. So this is how we are going to generate all the round keys. So we are going to generate all the round keys. Okay, so this is the formula wi minus 1. Okay, now if you see, so these are the examples. So we have given 128-bit cipher key agreed upon by Alice and Bob. Consider Alice and Bob are communicating by using this key. Now, how my key will be generated for the first round is, I'll take the first 4 bytes as one word. So this is w naught. Next 4, so 34, 75, 88 is, this is w1, 31, e2, 12, 00. This is w2, and this will be my w3. So if you observe w0 is equal to 24, 75, a2, b3, w01 is equal to 34, 75, 56, 88, w02 equal to 31, e2, 12, 00, w03 equal to 13, AA 5487. Okay, now when I want to get the values of w4, now here w4 mod 4 is 0, so I'll take t4, and I'll apply XOR with w0. I'll apply XOR with w0, then I'm getting w4. Like that, if I want to have w5, how I'm getting w5? So w5 mod 4 is not equal to 0. So I need to add wi minus 1. So I minus 1 is w4 XORed with wi minus 4, that is w1. If I do XOR operation between these two, I'll get this value. I'll get this value. So this is how the round keys are generated. This is how the round keys are generated. Okay. So how many round keys are required is n plus 1. So I'm considering an 128-bit key. I'm considering an 128-bit key. So how many round keys I need? 11 round keys. So this is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. As I told, the initial round key, that is W0, 1, 2, 3, it will be given to the pre-round transformation. That will be given to the pre-round transformation. Upon next, the remaining 10 will be given to the 10 rounds. Remaining 10 will be given to the 10 rounds. And finally, this is the AES original structure. This is the AES original structure. So you will be given an 128-bit plain text. Remember, you'll be given an 128 plain text. Now I told you, before the round starts, this 128-bit plain text will be given to an add round key. Add round key. Now this add round key after will give. Okay, so a plain text is 128. Before giving the add round key, it will be generated into a state or transformed into a state of size 4 by 4, and each element in the state is of size 1 byte. Is of what size? 1 byte, not bits here. 1 byte. It will be given. Now for this state, add round key will be applied. Then it will be given to the substitution byte, that is round 1. So in each round we'll have 4 transformations. What are those? Substitution byte, shifting rows, mix columns, add round key. After applying all these things, so whenever we're getting add round key, I told you, the first thing that you are considering, W0, 1, 2, 3 will be given to the add round key, 4 to 7 will be given to the round 1. Like that, everyone will do the operation. And one more point also I told you, the last round in the encryption will not have the mix columns. So if you see, this is the last round in the AES with 10 rounds. That is when you consider cipher key size as 128. If you have only 3 operations: substitution byte, shift to rows, and add round key. Shift rows and add round key. Okay, this is regarding encryption. This is regarding encryption. Now, if you consider decryption, here the order of the transformation that we apply is different. The order of the entire we different. So whenever at the receiver side we take the ciphertext, what is size of the ciphertext? Again, we are going to generate the 128-bit ciphertext from the encryption. This will be given to the receiver side. Again, we'll have 128-bit ciphertext. Now, this ciphertext again will be given to the round key. Now, you need to see the keys in order which we have applied here on the encryption, they will be applied in the reverse order in the decryption. So initially for the ciphertext at the decryption stage, the initial stage add round key is what? W40 to 43, whereas in the decryption it is W0 to W3. That's you need to remember. The round keys are applied in the reverse order. Now, if you see here, the first operation is substitution byte, shift rows, and then mix columns and add round key. But whereas here, if you see in the decryption, the first operation is inverse shift rows, inverse substitution bytes, add round key, and inverse mix columns. So these two operations are swapped. 1, 2, and 3, 4 are swapped at the decryption side to make them as invertible. Make them as what? Invertible. If you observe here, finally in the last round also, in the decryption also, it doesn't have the mix columns. It doesn't have the mix columns. So we'll have only inverse shift rows and inverse and substitution bytes and add round key. So I told at the initial stage, we'll call it as the inverse operations of substitution bytes, shift rows, and mix columns. We call it as inverse mix columns, inverse substitution bytes, inverse shift rows. But we call add round key as add round key only. Why? Because add round key is a self-invertible component. Self-invertible component. Now, this is how we are going to convert the given plain text into ciphertext by using AES algorithm. And this is how we are generating the keys. For example, consider if you are having the key as the key size as 256. 250. Now, how we are going to generate the round key? How we are going to generate the round keys? Now, here we'll take instead of mod 4, we'll take mod 8. We'll take mod 8. Here we'll take it as mod 8 operation, and we'll find out all the round keys. We'll find out all the round keys. Okay. Remember this process. Now coming to the analysis of AES. Coming to the analysis of AES. AES is more stronger than DES. So up to now, they have tried so many brute force techniques or known plain text techniques, but no one has cracked the AES. No one has cracked the AES. And there is one design in which they have altered design. This is the original design of AES. Later, some days they have altered the design of AES, where they have made the whatever the order of the transformation they apply in the encryption, in the same order they have applied in the decryption also, but making some changes. So when compared with DES, the advanced encryption standard is more secure. Okay. So with this, we have completed the second unit. Thank you so much.